So the x's are copied forward. The z's are left alone. The z's are copied backward. Like that. And so what we end up with is logical x1 has become logical x1 times logical x3. Logical x2 has become logical x2 times logical x4. And so at the logical level, what's happened? So how should I say this? You could probably say this more nicely. Oh, here, look at this. See if you like this. So I'll call this the encoding circuit for the 4-qubit code. So the encoding circuit takes 2 physical qubits and it outputs 4 physical qubits that are encoded into the code. Right? So that encodes into the first code block. This takes qubits 3 and 4. I'm just trying to write this in a nice mathematical way. Encoded into 4 physical qubits, and then we do transversal CNOT gates. Right, so this is an observation, I guess. And the claim is that this is equal to, that this implements a logical CNOT gate, and the way they say this mathematically is you just say this is equal to transversal CNOT gates on the encoded data, on the logical data, followed by the encoding circuits. So this diagram, like it commutes, or we can call it here. Does that make sense? So the encoding circuit, I don't know what it is, but it's some 2 to 4 qubit stabilizer circuit, which we could figure out. But yeah, so we take 4 logical qubits into, let's see here, okay. Is that clear? Okay. Yes, so I guess, so the point is, for CSS code, transversal physical CNOT gates are the same as transversal logical CNOT gates. Okay. If there's no noise. All right. And it's fault tolerant in this sense that it doesn't spread errors. Okay. Let me give some other examples. Right, so I guess actually this isn't very satisfying, is it? I mean, I've told you how to do CNOT gates, but I've only told you how to do CNOT gates. So that's because other gates are hard. Usually. I mean, so there's special cases, so I can do a couple of special cases. For example, for any self-dual CSS code. So self-dual means that the X stabilizers are the same as the Z stabilizers, except X replaced by Z's. So for like we saw the 7-qubit Steen code. So those are the X stabilizers, and the Z stabilizers are exactly the same. The X stabilizers commute with the Z stabilizers, so it's a valid code. So this is the 713 Steen code, and so the claim is that H. Oh, here, I guess I can do it again using this fancy notation. Maybe not. Okay, so if I encode into 7 qubits.
Why is it called 713?
Yeah, so it's 7 because there's 1, 2, 3, 4, 5, 6, 7 physical qubits. 1 because 7 minus 6 means that there's 1 logical qubit remaining. And 3 because the distance is 3 because I can correct any one error. So any one, for example, any single z error can be corrected because it'll have 7 distinct syndromes, or 7 different positions the z error could have occurred.
How do I know I cannot correct 2 errors?
You can't in this case because the code's perfect, or it's a perfect CSS code, meaning that for correcting z errors, you have 3 X stabilizers, which means there's 2 to the 3 possible syndromes.
Yes.
0, 1, 0, 1, 0, 1. And you have 7 bits, you have 7 qubits, so that's 1. So the possible errors are 1 because you could have no error
Yeah.
for the identity,
Yes.
plus 7 for the 7 different qubits. That's already 8.
Yes.
So
Yeah.
8 is equal to 8.
Yeah.
So yeah, there's no room, I guess, is the point. But yeah, it's a good question though to ask sort of for a code, how do you know what the distance is? I mean, it's not easy, right? You gotta like try all combinations of 1 error, try all combinations of 2 error until you get some syndrome collision or something goes wrong. It's a combinatorially involved thing.
Mm.
You can't just look at it. There's something else that's a good question.
It's a stark contrast to classical linear code, right? We can read off Hamming distance from the set of check metric from the
Not
rows.
really. I mean,
Yeah.
right? So it's. I think it's the same issue. I mean, so like it's easy if you have a CSS code. What you can do is you can compute the what's it called, the orthogonal complement. So this you can think of this as a binary subspace,
Yes.
and you can compute the orthogonal complement of that binary subspace.
Yes.
And you can do the same thing with a non-CSS code. You just compute the binary complement using the symplectic inner product instead of the standard
Yes.
inner product. And so that gives you the set of logical operators, the set of all logical operators for the code
Yes.
in a matrix form. So actually, what you'll get, you'll get a right. So in Mathematica, you just use the null space command. Right? The null space of a matrix is a dual, is a set of everything orthogonal to the matrix. So what you'll get is you'll get a set of generators, or for the dual, or you'll get a set of generators for the logical operators.
Mm.
But the problem is you don't know what the least weight logical operator is.
Yes.
Because it could be some complicated combination of the generators,
Mm.
or like, so it's not one of the rows you're given, it's some linear combination of the rows that you're given.
Mm.
But also the least weight logical operator could also involve the stabilizers.
Yeah.
I mean, for example, with this code, logical x, I'll use a bar notation. Logical x is x, 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 x. Logical z is, but it's not as distance 7 code,
Yes.
because even though this generates the set of logical operators, if you multiply this by one of these stabilizers, you get a weight 3 operator, like x, 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 I. And so that's not obvious. It's something you just have, as far as I know, it's something you just have to try in Mathematica, or like try all combinations and find the least weight one. Yeah. Okay.